This lesson is part 2 of section 2.3 on the techniques of differentiation. Our objective for today is, again, the same as yesterday's. We want to use the product rule and the quotient rule to find the derivatives of products and quotients. We're going to begin, though, by actually proving the quotient rule, which is something we did not do in our previous lesson. So let's start off first with our proof. We have let y equal f of x over g of x. Now, by the definition of the derivative, we can say that the derivative of y with respect to x is the limit as h approaches 0 of f of x plus h over g of x plus h minus f of x over g of x all over h. Now, if we try to evaluate this limit, we plug in 0 and we end up with f of, x plus 0, so f of x over g of x minus f of x over g of x all over 0. So we end up with 0 in the numerator and 0 in the denominator. So we have this indeterminate form once again, and we cannot evaluate this limit. So once more, we need to algebraically manipulate this so that we can evaluate our limit. So I will rewrite this as dy dx is equal to, now this difference quotient I want to rewrite as well. So if we were going to try to combine these two fractions here, we would need a common denominator, which means in the first term I'd have to multiply by g of x over g of x, and in the second term I'd have to multiply by g of x plus h over g of x plus h. Okay, then since everything is divided by h, since I have that common denominator now, I can just add that to the denominators for both of those terms as well. So if I rewrite this just by simple, algebraic simplification here, I end up with g of x times f of x plus h minus f of x times g of x plus h all over that common denominator g of x times g of x plus h. And then since that's divided by h, I'm just going to bring this up here, say that it's multiplied now by h as well. Okay, so if I tried to evaluate this limit now, even if I try to plug in 0 one more time, I will still get that indeterminate form 0 over 0. So I need to do some further manipulations here to try to get that to be something that I can actually evaluate. I can't evaluate this quotient as is. So what I'm going to do is add and subtract the same value, that same expression, just like we did in the previous proof with the product rule, because that will allow me to manipulate the numerator a little bit and then start factoring out some parts. So what I'm going to do is take the expression g of x times f of x, and I will add and subtract this to the numerator, so I'm really only adding 0. Okay, so as you can see here, I did add and subtract the expression g of x times f of x, so I'm really just adding 0. But what that allows me to do now is to factor the numerator, because I have a common factor of g of x in the first two terms and a common factor of f of x in the second two terms. So we can rewrite this, and it is the same as the limit as h approaches 0 of g of x multiplied by f of x plus h minus, oops, that's supposed to be f of x. Okay, and then from the second two terms, I'm going to do something a little bit strange here. I'm going to factor out a negative f of x, okay, instead of f of x here, because then I can switch the signs in front of the g of x plus h and the g of x to make it look more like this term here. So we have that multiplied by g of x plus h minus g of x, okay, all over g of x times g of x plus h times h. Okay, so we've only got one more algebraic manipulation now that involves moving this h out of the denominator here. And then once we do that, we can actually evaluate this limit. So I'm kind of running out of room. I'd rather just pause the video here and then show it off to the right. And then you can kind of clearly see exactly what's going on here to evaluate the limit. Okay, so if I rewrite this limit now by bringing up the h from this denominator, it was here before, and I just bring it into both terms in the numerator here, now I've just created an expression here. This is the difference quotient of f of x and the difference quotient for g of x. So if you evaluate the limit now, remember limit rules allow us to break down products and rewrite that as the product of two limits. So I'm just going to go ahead and just evaluate this limit by plugging in h is 0. So we end up with this whole limit here is going to equal g of x multiplied by, this is simply the derivative of f of x, right? This is how we define the derivative of f of x when we evaluate the limit as h approaches 0. Then we have minus f of x times the derivative of g of x all over g of x times g of x. So you can clearly see we have the quotient rule. This is ho d high minus high d ho over ho ho. And thus, concludes our proof. Okay, so a nice result of the quotient rule is something we call the reciprocal rule. So the reciprocal rule is for some kind of function of the form 1 over, I'm going to call it h of x, just because we keep using f of x and g of x, and I think that's kind of confusing. So anything of this particular form, we can find the derivative very quickly by using the reciprocal rule. So using that quotient rule that we just came up with, if we let f of x equal 1, then that means that f prime of x, okay, is equal to 0, right? So just by using the quotient rule and substituting, if we want to take the derivative with respect to x of f of x over g of x, okay, and f of x is equal to 1, now we have a reciprocal, right, 1 over g of x. Well, just by those appropriate substitutions, we find that we end up with the opposite of g prime over g times itself, so g squared. In other words, let me just use the function notation here, g prime of x over g of x times g of x. Okay, so hopefully I haven't completely confused you with this change in notation, but basically if you have a function that's a reciprocal, like for example, this is 1 over x, then to find the derivative of 1 over x, we need to take the derivative of the bottom, so the derivative of the bottom here is 1, okay, and we're going to make that the opposite of that derivative, so negative 1 all over the function, the denominator, times itself. So we have x squared. So the derivative of 1 over x is negative 1 over x squared. Now you can verify this if you wanted to, just in case you weren't sure. Let's rewrite f of x as x to the negative first power. So by the power rule here, we can write that as negative 1 times x to the negative second power, which is clearly negative 1 over x squared. So we do end up with the same derivative, okay, as if we just use the reciprocal rule. Now in example 2, if we want to find the derivative of 1 over x cubed, so we want to take the opposite of the derivative of the bottom. So we have negative 3x to the second power. Oh, why did I write a 3 even though I said to the second power? All over the bottom times itself. So we have x to the third times x to the third, which gives me x to the sixth. So if I simplify here, we get negative 3 over x to the fourth. And once again, if I wanted to verify this, I could write that function as x to the negative third power. And if I differentiate this, we have negative 3 times x to the negative fourth, or negative 3 over x to the fourth power. Okay, so once again, the exact same derivative. Okay, in the next example, we're asked to find the derivative of a quotient, and we're asked to do this using 3 different methods. In your homework, you will be asked the same kind of question. You won't have to do it on every single problem, but on several problems, we will ask you to do it 3 different ways so that you get comfortable, and basically you start developing ways of being efficient on tests and quizzes. You'll identify when it's good to use those, a different method, and when it's more efficient for you just to simply use the quotient rule. So we're going to start off first by using the quotient rule here. So the derivative, f prime of x, will be ho, so x squared, times d high, so 3x squared, minus high, d ho, all over ho ho, so x squared times itself. All right, so let's algebraically simplify. We have 3x to the fourth minus 2x to the fourth plus 2x all over x to the fourth. So if we simplify, the derivative here is going to be x to the fourth plus 2x over x to the fourth, and we can rewrite that as 1 plus 2 over x cubed. All right, now if we try the product rule, this time I'm going to rewrite this as x cubed plus 1 times x to the negative second power. So if we use the product rule here, we take the first and we multiply it by the derivative of the second. So let me rewrite this, sorry. So the derivative here would be x cubed plus 1 times the derivative of the second, so negative 2x to the negative third power. Then remember we have to add to that the second multiplied by the derivative of the first, so that's just 3x squared, and then we would simplify here, so we end up with term we have to distribute to these two here. When we multiply negative 2x to the negative third times x cubed, we get just negative 2 because the x cubes end up canceling one another out, x cubed over x cubed. Then we end up with, in the second term, negative 2 times x to the negative third power. And over here, since those x that x squared over x to the negative, or x squared times x to the negative second power ends up also canceling each other out. We end up with just 3. So we have 1 minus 2 over x cubed, which is the exact same thing. Oh, shoot. You know what I did? I know what I did. Come back here. Yep. Okay, so I just did this real quick and I didn't even really pay attention to the signs. When you have to subtract away this product here, you are really technically distributing it to both terms, and I did not do that here. So I did basically what I tell you guys to avoid mistake of. I just showed it to you here, so I guess that's a good thing because it's easy to do. Just be really careful about not making that mistake. So this ends up being 1 minus 2 over x cubed. So sorry, I must have been just so in the zone and hyper focused that I just sort of was talking at the same time and forgot to remind myself to do that. So all right, so we found the same derivative, and then now let's work on just simplifying at first algebraically and then finding the derivative. Okay, so here if we take our function and we try to simplify this, x cubed plus 1 over x squared is the same as x plus 1 over x squared. Now if we differentiate that, that's actually a lot easier for us than using either the quotient or the product rule. And like I said, you want to find efficient ways of finding the derivatives of functions. So we end up with the derivative of the first term, which is simply 1, and then plus the derivative of the second term. Now when you take that derivative, you can use the reciprocal rule here, so let's practice that. We're going to take the opposite of the derivative of the bottom, which is going to be 2x, and then divide that by the bottom times itself. So we have x to the fourth. So if we simplify, that derivative is 1 minus 2 over x cubed, which is the same as the last two derivatives that we found. So that's how you can find the derivative of a quotient using 3 different methods: the actual quotient rule, the product rule, and simplifying algebraically before you begin to use any method. Okay, so the last part of this lesson is going to focus on being able to gather information from a graph to answer specific questions pertaining to derivatives. So here in number 4, we say that f and g are functions with the graph shown to the right, and we're going to let u of x equal the product of f of x and g of x, and v of x is going to be the quotient of f of x and g of x. So our very first problem asks us to find the derivative of u, and because u is a product, we can use the product rule here. So u prime of x is going to be the first, so f of x multiplied by the derivative of the second, g prime of x, plus g of x, the second, multiplied by the derivative of the first. So that's u prime of x. So that's just in general terms. Now we can use that in order to find u prime of 1. Okay, so here's where the graph comes into play, because if we want to evaluate the derivative at x equals 1, then that means we need to find f of 1. We need to find g prime of 1. We need to find g of 1 as well as f prime of 1. All right, so by looking at the graph here, we can find all of these values. Let's work on the easy ones. F of 1 is going to be pretty easy. That's just 2. Okay, f of 1 is 2. And g of 1 is also another easy one. G of 1 is 1. Now, when we talk about the derivative of g at x equals 1, we're looking at the slope of a line that would be tangent to the graph at x equals 1. Now, the slope of that line is simply the slope of that linear function here, which is going to be negative 1. So g prime of 1 is negative 1. Now for f prime of 1, we're looking at the same thing. This time it's supposed to be tangent to f at x equals 1. So the line that's tangent to f at x equals 1 has the exact same slope here, which is a slope of 2, right? Up 2, right? Over 1, yeah. So f prime of 1 is 2. So if we evaluate negative 2 plus 2, we get 0. So u prime of 1 is 0. For v prime of x, we use the same idea that we used for u prime of x, this time that we're dealing with a quotient, so we'd have to use quotient rule. So we have ho d high minus high d ho all over ho ho. So when we want to find, let's label that as v prime of x. So when we want to find v prime of 1, now we have to take all of those, and evaluate it at 1. So g of 1, f prime of 1, minus f of 1 times g prime of 1 all over g of 1 squared. So I would like you guys to try that on your own and then just check with the key real quick to make sure that you understand how you're going to plug in those values. All right? All right, the next question here is, I think, a pretty cool problem because it really requires you to understand continuous and differentiable functions. So we're going to use this diagram here to answer all of the questions. Now, the first one says, find the intervals where f of x is continuous. So here's the graph of f of x to the right. Now, f of x is continuous in this portion of the graph, so we're going to say from negative infinity all the way up until 0. We will not include 0 though, because here we have a jump discontinuity, okay? But the function is again continuous from 0 up until 1, where we have a vertical asymptote. Again, we will not include 1 because we do have a vertical asymptote here on the graph of f of x. Now it picks back up with the continuous values, once again from 1 to, it looks like 2, because here we have another jump discontinuity. So we have from 1 to 2, and then from 2 and to positive infinity. Okay, so these are the values for which our function is going to be continuous. Now for part B, it asks us to find the values of x where your function is not differentiable. So remember, in order for a function to be differentiable at a certain value, it has to be continuous at that value. So the fact that we just answered part A makes it really easy for us to answer part B, because everywhere the function is not continuous, it is also not differentiable. So we can say real quick 0. It's not continuous at 0, which means it's not differentiable at 0. It's also not continuous because of that vertical asymptote at x equals 1. And it's not continuous at x equals 2 either, because we have another jump discontinuity. Now, the only one that's kind of a little trickier to remember is that when you have a cusp, like we have at -3 here, the function is also not differentiable, because remember, those tangents here, the slopes, they do not end up approaching the same value. They go towards negative infinity and positive infinity. So we have a vertical tangent here, okay? Now in part C, we want to find all intervals where our derivative will be positive. So we can just do this graphically. You're going to look for all the parts on the graph where you'll have a slope that will be positive, or I'm sorry, the tangent slope will be positive. So for example here, if we look and we try to draw in tangent lines here, from -3 to 0, we'll always have positive tangents, always, okay? And from, it looks like from 2, okay, up until you get to 3 here, we'll also have positive tangents. So from 2 to 3, okay? Now those are open intervals, they are not closed intervals. One, because it's not differentiable here at x equals 0, and also because the tangent here, or the slope here, is actually 0, okay? Now, on the intervals where the derivative is negative, you're looking for the opposite thing. You're looking for slopes that are going to be negative. So we want to draw in some tangents here, and we see that from negative infinity all the way up to -3 here, we have negative tangents, or slopes of tangents that are negative, okay? And from 0 to 1, same thing, okay? We'll have negative slopes there. So from 0 to 1. Then we pick back up one more time. From 1 to 2, we'll have a bunch of negative slopes here as well for those tangents. And that would be 1 to 2. Okay, and then finally from 3 beyond, so from 3 to positive infinity. So these are all the intervals. These are all open intervals. Now, part E asks for the values where f prime of x is 0. So we want to know where our derivative is 0. So that means we have a slope that is 0, meaning our line would be horizontal, our tangent's horizontal. So that only happens right here at x equals 3. So at x equals 3, our derivative is 0. Okay, now in part F, it asks us to find the values of x where your function is continuous but not differentiable. Remember, that happens when you have corners or cusps in your graph. So we're looking at a place here where the function is clearly continuous because it is defined at x equals -3, but it is not differentiable there. So at x equals -3, our function fails to be differentiable even though it is continuous. Now, in part G, we're asked to find the values of x where your function is differentiable but not continuous. Now, at first, this might look like a subtle difference, but this is a huge difference. Here, they're asking for where the function is differentiable but not continuous, and you should automatically say nowhere, okay? This isn't possible. A function has to be continuous in order for it to be differentiable. So there are no values of x where the function is differentiable but not continuous. All right, my fine mathematicians, we are done with this particular lesson. So make sure you come into class asking good questions and be ready to work. Nice job. See you mañana.